All right, welcome back. For today's class, we are going to quickly recap the mean and median take-home problems that I gave you from last class. We'll look at those first, and then we will move into learning more about range, standard deviation, and finally understanding how to apply the z-score formula to real-world application problems. That will conclude all of 096. Okay, so let's take a look, finish our notes today. All right, let's do it. Example 3 that you were to take home with you, you were asked to find the mean and the median for each of these examples. I am hopeful that for each of these you wrote out your data values from smallest to largest, and then to find the median you identified the exact middle value. So as we notice here, these go away, these go away, these go away, and you see that 8 happens to be the exact middle. So the median for our sample is simply 8. In order to find the mean, we know that that is the average of all of the numbers. So you are going to add each of these values up, and you divide by the total number of values you had. You should have had 7.7. Do the same things for the next two examples. You should have found that your median was 48.5 and your mean was 53.8. And for your last problem, your median was 8 and your mean was 7. So I'm hopeful that your work agrees with mine. Let's turn the page so that we can continue with range and standard deviation. So we have something called measures of variation. So first off, I want you to look at the distribution of chocolate chips in this particular chart. We have two different types of cookies. We have regular Chips Ahoy, and we have something called Bond cookies. Now, what we've illustrated here with this diagram is for each of these points here that represents the number of chocolate chips in that particular cookie, right? So for instance, in our first cookie, we notice we had 18 chocolate chips, okay? So essentially it's like saying, let's map out how many chocolate chips are in each of these cookies. Notice that you had 1, 2, 3, 4, 5 cookies that all had 20 chocolate chips. Notice you had 1, 2, 3, 4 cookies that all had 22 chocolate chips, and so on and so forth. Notice that the smallest number of chocolate chips were 18 in a Chips Ahoy cookie, and the greatest number of chocolate chips in a cookie was 30, and that's specific to Chips Ahoy. Now, if you look at Bond cookies, do you see how they're more consistent? You have way more cookies that are in the 23 to 25 range in terms of the number of chocolate chips. And I apologize, I meant 19, not 18. So notice with your Bond cookies, you're more consistent, right? You're expecting that if you take one of those delicious cookies and you eat it, you're going to have anywhere from 23 to 25 chips in each cookie. Whereas with Chips Ahoy, you can get an assortment of values. So that's going to lead us into this idea of measures of variation in terms of range and standard deviation. Notice we have our formula here that the range is your maximum data value minus the minimum data value. So we want to first identify the ranges of the Chips Ahoy and the Bond cookies above. So we're going to start with Chips Ahoy. So let's go ahead and write Chips Ahoy. And to determine the range, we're going to take the cookie with the greatest number of chocolate chips, and that is 30 chocolate chips. And we're going to subtract the cookie with the smallest number of chocolate chips, and that is 19. When we take the 30 and we subtract the 19, you should have that the range is 11 chocolate chips. We're going to do the same thing for Bond cookies. Notice the range will go as high as 25 chocolate chips to as low as 23 chocolate chips. So the range is 2. So essentially, notice that the 11 essentially tells us that there's a variation of 11 chocolate chips from the greatest to the smallest. So there's a lot of variability. Whereas with our bond cookie, since our range is only 2 chocolate chips, only 2 chocolate chips tends to separate the largest from the smallest. So you know that you're way more consistent when it comes to the bond cookies. Hopefully that idea of range is very clear in terms of describing the spread of the data. Next, standard deviation is a measure of the spread of the data that incorporates the distance that each data point is from the mean of the data set. That's very, very important. Standard deviation is essentially telling us how far are we from the mean. Okay? I would like you to note that small s, lowercase s, is a symbol for sample standard deviation. And I want you to notice that our Greek letter sigma, notice it's kind of like a 6, but it's flattened. It's like that 6 tail is flattened, it's nice and right. So you have your sigma with the flattened 6 here. Sigma is the symbol for a population standard deviation. Let's turn the page and I'll show you how to find it. First, we have the formula for the standard deviation of a sample. S is equal to the square root of the sum of the differences between the raw data value and the mean squared divided by the number of values we have minus 1. If we wanted to, for instance, and I'm just going to write this here for your reference, if you want the formula for the standard deviation for a population, it would look almost identical, right? First off, S would not be S. In this case, it would be sigma, right? And the formula is only slightly different. So we still are adding all the squared differences. Oops, we don't need that there. X minus X bar squared. But this time we're dividing it by n instead of n minus 1. So with our sample, we divide by 1 less than the total number of values we have. For the population, we divide by the total number of values we have. So I'm going to walk us through only one of these problems because essentially they're both identical in the process. I'll do one and you can take the other one home to try it on your own. So for example 6, we want to find the mean and the standard deviation for the following set. The first thing we are going to do is let's calculate the mean by adding all of our values. So we have 2 plus 3 plus 6 plus 7 plus 9 plus 3. And if it's helpful, I can go ahead and write that down. 2 plus 3 plus 6 plus 7 plus 9 plus 3. Add all 6 of those values together. And after you add all 6 of those values together, you get 30. And then you're going to divide by 6. So your mean in this case is 5. Next, because we want to calculate standard deviation by hand, what I'd like to do is walk you through a process that you can use to help you find the standard deviation for any set of data. We're going to start off by constructing a chart. So our first column is simply going to be our X values, our raw data values. So our raw data values in this case are 2, 3, and if you want, we could write this in order. So 2, 3, 3, 6, 7, 9. 2, 3, 3, 6, 7, 9. We can start there. Notice in our formula, we have X minus X bar. So our second column, we're going to call X minus X bar. As a reminder, X is our raw data value, and X bar represents our mean. In this case, our mean is 5. So for our first cell here, we're going to take our raw data value and subtract the mean. So 2 minus 5 is negative 3. Let's do it again. 3 minus 5 is negative 2. 3 minus 5 is negative 2. 6 minus 5 is 1. 7 minus 5 is 2, and 9 minus 5 is 4. The column header should guide your calculations. Because this says X minus X bar, just think about it logically. You'll take each raw data value and you'll subtract the mean. Next, notice in our formula that x minus x bar is being squared. So that's our next column header. You're going to take each of the differences and square them. So think of it logically. Negative 3 times negative 3, well, that has to be a positive, right? So negative 3 times a negative 3 is positive 9. Negative 2 times a negative 2, positive 4. Again here, 1 squared or 1 times 1 is 1. 2 squared or 2 times 2 is 4. 4 squared or 4 times 4 is 16. Excellent. So the first thing is we listed our raw data values. Our second step was to subtract the mean from each of our raw data values. Our third step was to square each of these values. Remember that when you square a negative, it always becomes positive. So that's why we have no negatives here. Notice for our formula, we have this Greek letter sigma, capital, right? So sigma in this case means to add everything up. So we are going to add all of our values. Okay, so what I'm going to note here is that sigma x minus x bar squared is equal to, remember, this is just the total of everything. So we have 9 plus 4 plus 4 plus 1 plus 4 plus 16. So essentially we should have 38. So 9 plus 4 plus 4 plus 1 plus 4 plus 16, again, just double checking, is 38. So we just figured out the sum of this column, the sum of all of our squared differences. Next, according to our formula, we're going to notice that the S, our standard deviation, is found by taking the square root of the sum of our squared differences, which is 38, divided by the number of values we have minus 1. So 1 less than the total number of values. In this case, we have 1, 2, 3, 4, 5, 6. So our n is equal to 6, which means n minus 1 is equal to 5. So what I would urge you to do is when you take your calculators, you could do this in two ways. You can simply take 38 divided by 5. So you have 7.6. And then you could say, well, let's take the square root of 7.6. So second x squared, 7.6, enter. So we have just found that the standard deviation, and let's say we round to the nearest tenth, so our standard deviation is 2.8. And there you have your solution. At home, I would like you to follow this same format, this same exact process. For example, number 7. So I'm going to write at home. Okay? Another way of punching this in is you can say, let's do the square root. So second x squared, that's how you get the square root. Notice you see the square root key above my x squared button. So the square root of, and then we could put 38 divided by 5 and then close the set of parentheses. So this way our calculator knows we're taking the square root of this value, 38 divided by 5. Press enter and that gives us 2.8. Okay? Wonderful. As always, if you have any questions about this process, feel free to ask. Nicole, hopefully that answered your question. If it didn't, please be more specific with that question so I can look at what it is that you're trying to figure out. Okay. In terms of n, recall that n is the number of values. So we had 1, 2, 3, 4, 5, 6 values in our set. We had 6 values in our data set. So n minus 1 means 1 less. Perfect. So you will do example number 7 at home. For number 7, you also need to find the mean and the standard deviation for the following sample data set. So we have 12, 7, 9, 5, 6, 7, 10. Give that your best shot. Let's see how you do. And just for your reference, consider that n, the number of values in your set, you just have to count how many number of values. So in this case, we have 1, 2, 3, 4, 5, 6, 7. So n in this case is 7. And I want you to take it from there. And no problem, Nicole. Perfect. Let's turn the page. Next, let's talk about measures of relative position. So we have something called the z-score. It's also called the standardized score. So your z-score in words is essentially when you take your data value and you subtract the mean, and then you divide it by the standard deviation. Now the cool thing is that the formula does not change. The notation does if you're talking about a sample versus a population. So for your reference, if you're working with a sample, you know that the mean is x bar and your standard deviation is s. For a population, you note that your mean is mu and your standard deviation is sigma. But the idea is here. So I want you to really think about this. To find the z-score, you're going to take your data value, whatever that is, you're going to subtract the mean, and then you're going to divide by the standard deviation, whatever that value is. I also want you to consider that implies that we have 1, 2, 3, 4 unknowns in your equation. As long as I give you any 3 of the 4 unknowns, you can always find the 4th. And I'll prove that to you with the examples that are ahead. Note here, you should always round your z-scores to the hundredths place. So 2 decimal values, okay? So 2 decimal values to the nearest hundredths place. Okay, let's try a problem and see how this works. A sample of fish was obtained from Keuka Lake. If the mean length is 14.2 inches, by the way, as I work through these problems, I'm always either underlining or writing pieces of information down just so that I kind of collect all of that and keep it organized. So for instance, for me personally, when I see mean length is 14.2 and I know I'm talking about a sample, I'm going to write that the mean x bar is 14.2 inches. That's going to be helpful in terms of organizing your information. So the mean length is 14.2 inches with a standard deviation of 2.7 inches. So again, standard deviation for my sample is S, and we know that standard deviation is 2.7 inches. Next it says, what is the z-score? So we don't know z, so I'm going to put z is question mark. For a fish that is 18 inches long. There are 4 unknowns in every z-score formula. Z, x, x bar, or s. We don't know z. S is 2.7. X bar is 14.2, which means 18 inches must be x. So we'll write that x is 18, in which case 18 represents our raw data value. So let's plug it in. Z is equal to x minus x bar all over the standard deviation. Do this piecemeal. You'll do 18 minus 14.2 first, just to start off. That gives you 3.8. Then you'll take 3.8 and you'll divide that by 2.7. When you punch this into your calculator, you get 1.407407407. We want to round to 2 decimal places, or to the nearest hundredths place, which means our answer is going to be 1.41. And that is our standardized score. A fish that is 18 inches long has a z-score of 1.41. Let's do it again. All of Professor Smith's exams were graded. The population mean score is a 72 points with a population standard deviation of 4.9 points. So the mean score in this case for population, mean is mu. Our mean is 72. And our standard deviation, which is that 6, right, but with a flat tail. So our standard deviation, or sigma, is 4.9. So 72 points and 4.9 points. If Nick scored a 65, what is his standardized score? We know that z-score is also called standardized score. So that means z is unknown. We don't know it. But what we do know is that x must be the raw data value. It must be 65. So we use z is equal to, we use the same exact formula. The raw data value minus the mean divided by the standard deviation. Even though we have different notation here for mean and standard deviation, that doesn't change the formula. Raw data value minus the mean divided by standard deviation. Boom, done. Don't overthink it. Next, we have 65 minus 72. That'll give us -7. Then take -7 and divide it by 4.9. When we do this, we get a z-score of -1.43. And I'm going to show you what I have punched into my calculator. When we took the -7 and divided by 4.9, we had -1.4285, etc. So round to 2 decimal places, -1.43. And that's our z-score. Excellent. Let's turn the page, try some more problems. Number 10. Bill earned a 1240 on the SATs where the population mean, again, see how I'm going to underline everything, where the population mean was a 1050 with a standard deviation of 100 points. Ted earned a 27 on the ACTs where the population mean was a 21 with a standard deviation of 2.8. Who has a higher standardized score? Now, the cool thing is, once you figure out who has the higher standardized score, essentially it tells you who did better on their respective assessments. While you know and you're probably thinking the SATs are very different from the ACTs, we are standardizing them so that way we can compare apples to oranges. We're essentially putting them on the same scale. By standardizing them, we're looking at them in terms of z-scores, so we're able to say, okay, who did better than who? Let's take a look. I want to organize my information by writing out 2 columns, SATs and ACTs. For my SATs, I know that my population mean was a 1050. And I know that my standard deviation was 100. We also know that Bill earned a 1240 on his SATs. So his raw score was 1240, which means we don't know Z. Now I want to go to the ACTs. According to our information, we know the mean is 21 and the standard deviation is 2.8. We're also told that Ted earned a 27, so his raw score on the ACT was a 27, which means we need to calculate our z-score. So, according to our formula, we have z is equal to x minus the mean divided by the standard deviation. Let's compute the numerator. So we have 1240 minus 1050. That gives us 190. And then 190 divided by 100, well, that gives us a z-score of 1.9. Let's do the same thing, but this time for Ted, who took the ACTs instead of the SATs. Z is equal to his raw value minus the mean divided by the standard deviation. 27 minus 21, well, that's just going to give us 6. And then we're going to take this 6 and divide by 2.8. That gives you a z-score of 2.14. Here we had 1.9. Because we round z-scores to the nearest hundredths place, there is no second value in our hundredths place, so I'm just going to write 0. Bill Bill's standardized score was a 1.90 and Ted's standardized score was a 2.14. So, according to our calculations, Ted had the higher standardized score. So essentially what I want you to think about in terms of standardized score is that with respect to the rest of the population who took these tests, Ted outperformed Bill with respect to the rest of the population. So since Bill only had a 1.9, which is great, right? It's higher than the mean. Ted earned a much higher score with respect to the rest of the population. So Ted did better with respect to the rest of the population. Hopefully that's clear. Let's look at number 11. The mean height of 10-year-old American girls is 54.5 inches with a standard deviation of 1.89 inches. If Janine has a standardized height of z is equal to negative 1.46, what is her height? And we want to round to the nearest tenth. So as you read through this problem, I notice the first thing you guys are saying is that the mean height is 54.5 inches. Now remember, we're talking about 10-year-old American girls, so is this a sample or a population? If you said population, you are correct. So we know that the mean height, mu, is 54.5 inches with a standard deviation of 1.89 inches. So sigma is 1.89 inches. Now Janine, one person in particular, has a standardized height of z is equal to negative 1.46. So z equals negative 1.46. Essentially what this implies is that Janine is shorter than the average 10-year-old girl. What I would like to kind of illustrate to you very briefly is that all of these z-scores are based on something called the normal curve, where your mean, your median, and your mode are the center of the data. So your mean is here at 0, your z-score of 0. And you'll essentially look at the spread of data with your z-scores ranging anywhere from -4 to +4. But as we illustrated, we look from the scale -3 to +3. But obviously you can have values in either tail. Okay, so visually this is what it would look like. So if Janine has a height of z equals negative 1.46, Janine is approximately here, which means if the mean is a z-score of 0, then she's shorter than the average 10-year-old girl. She falls below. Her height falls below that of the average. Hopefully the visual is helpful. Which means when it says what is her height, that means we don't know x. So we're going to use the same formula, except this time, and I'm going to rewrite the formula just so that you have it, except this time we don't know our raw data value. So let's plug in our information. Z is negative 1.46. Our x, we don't know it, it's unknown. We know our mean is 54.5, and we know our standard deviation is 1.89. So at this point, all we have to do is solve. What I would urge you to consider is that we actually have a proportion. A proportion is when you have a fraction equal to another fraction. This is something we covered way back in Unit 1, actually, when we discussed ratios and proportions. So back in Unit 1, when we had a proportion, a fraction equal to a fraction, we were allowed to cross multiply to solve. So I'm going to go ahead and circle what it is that we're going to cross multiply. Okay? So here we have 1 times x minus 54.5. So 1 times this expression is x minus 54.5. And then we have in our other bubble negative 1.46 times 1.89. Negative 1.46 times 1.89 gives me negative 2.7594. I'm not going to round yet. I want to wait to round until I'm all the way finished. So next I'm going to add the 54.5. And Brittany, thank you for sharing that answer. Let's see how it compares to mine. So we add the 54.5 and we get 51.7406. Excellent job, Brittany. That's exactly correct. Because we want to round to the nearest tenth, what we can say is that Janine has a height of 51.7 inches. And we have just answered example number 11. Notice we still use the z-score formula, but the only thing that we're missing this time is the actual raw score. What Janine actually scored in terms of her height, like what is her actual height. Plug in all the other values, and all you have to do is solve. Let's turn the page. Try a couple more problems. Number 12. The mean weight of an adult Labrador Retriever is 72.3 pounds. Because we're implying that the average of all the adult Labrador Retrievers are 72.3, I would hope that you notice that this is definitely based on population statistics. So the mean weight, mean is mu, right, is 72.3 pounds. Jack was told his Labrador Retriever has a standardized score of 1.45. So we know his standardized score, which is another word for z-score, is 1.45. We're also told that he weighs 77.6 pounds. Because we know his raw score, his actual weight, that represents our x, our raw data value. And that's 77.6 pounds. Then it says, what is the approximate standard deviation for the weight of an adult Labrador? What that implies is that we don't know the standard deviation for this population. So we're going to go ahead and note that the standard deviation is unknown. When we answer this, we want to round to the nearest hundredths. Fortunately, because we're talking about normal distributions, hence the standardized score, we're going to use the z-score formula. So z is equal to the raw data value minus the mean divided by the standard deviation. The z-score is 1.45. Our raw data value is 77.6. Our mean is 72.3. And our standard deviation is unknown. So I'm just going to leave it sigma, if you're okay with that. We still have a proportion. Okay? So essentially, we are still able to cross multiply. What you may notice is that we can combine like terms. So why don't we combine like terms first? 77.6 minus 72.3 gives us 5.3. 1.45 is equal to 5.3 divided by sigma. Again, we still want to solve. So since we have a proportion, let's go ahead and cross multiply. 1.45 times sigma is 1.45 sigma, and 1 times 5.3 is 5.3. We want to solve for sigma, so since it's 1.45 times sigma, we're going to divide both sides by the coefficient in order to get sigma by itself. When you take 5.3 and you divide it by 1.45, you get a value for sigma of 3.655, etc., etc. According to our word problem, it has asked us to round to the nearest hundredths. So two values or two places after the decimal. So to the nearest hundredths implies that our standard deviation for the population would be 3.66 pounds. And there you have it. So the standard deviation for the weight of an adult Labrador Retriever is 3.66 pounds. We have one question left to round out our notes, so why don't we just do that one together? The mean 096 final assessment score from fall 2019 was an 81.5. Okay, so the mean 096 final assessment score, so this is from all the students who took 096, their mean score was 81.5. So I'm going to use population parameters as well, because we're not talking about one class, we're talking about all the students who took 096. So we have 81.5 as our mean. We are then told it has a standard deviation of 3.2 points. So standard deviation of 3.2 points. If a student received a standardized score of 2.50, what was that student's score on the 096 final assessment? Standardized score refers to your z-score, and the z-score is 2.50. So I want you to just recognize right now that because that student got a z-score of 2.50, it's in the upper part of our normal curve. We know that that particular student scored really, really high. They did very well with respect to the rest of the students who took that assessment. Okay, so let's figure out what that student got on his or her 096 final assessment. So we have z, which is 2.50, is equal to x, the raw data value, which we don't know, minus the mean, which is 81.5, divided by the standard deviation, which was 3.2. Same thing, we have a proportion, so let's go ahead and cross multiply. 1 times x minus 81.5 is x minus 81.5. And then we have 2.50 times 3.2, which gives us 8. We add the 81.5, and we note that x is 89.5. So we can say that student earned a score of 89.5% on their 096 final assessment. We are done. We have officially finished all of our guided notes for Math 096. Congratulations, you made it to the end of the course. On Thursday, since there's no need to meet on YouTube anymore. Excellent job, everyone. Please stay safe, please stay healthy, and I will see you all on Thursday via Zoom. Bye, everyone.